Right. Basically, what we will do now is whatever we have studied,
Hmm.
we will draw the graph of a diode when it is forward biased, reverse biased. So in the y-axis, you will have current, and in the x-axis, you will have the voltage. So these are the two biases. These are the two ways a diode is used. Not open up, but no, I have. Okay. See this diagram.
Hmm. Yeah.
Okay. So we had studied last time if P is connected to P,
Hmm.
right? P side. So the representation of diode is this. This ये triangle दिख रहा है? If you see this triangle,
Yes.
okay, the triangle represents P, and
Okay. Hmm.
the line represents N.
Hmm.
Okay, this is the diagram. So what you've done is you've connected the P and junction. So that P and N were joined together by some method in factory, and it resulted in formation of a junction diode inside that PN
Done.
chip, right?
Okay.
And what we do then is we don't use a PN chip just because it has a junction potential inside it. We use it in two ways. One is by connecting the P side to the positive terminal of the battery,
Hmm.
right? So this results in very high conductivity of the device. It will conduct very nicely if you connect the P with P. But if you connect P
Hmm.
with N side,
Negative.
negative side, then it doesn't conduct. It offers infinite resistance. It will not conduct, hardly conduct. So we call
Hmm.
it reverse bias, okay? Because what we are doing here is we are actually uh, help opposing the junction potential which has been created inside it naturally. When you connect P and N together in the factory, a junction potential arises, which हमने पढ़ा था, depletion region gets created. Uh, Holes want to go towards the other side. They result in recombination, and the N side, the electron wants to go to the other side, and then they neutralize. Holes neutralize electrons, and electrons neutralize the holes on the other side, resulting in a region where only ions are left then, right? And that region is called as a depletion region. And because there
Hmm.
are ions in it, there is an electric field between the ions, the pentavalent impurity and the trivalent impurity. The ions are left out, arsenic, boron, there is an electric field. And the potential between the electric field is the called as the junction potential.
Hmm.
Okay? That is
Yeah.
what, right? So, but you don't use it, a diode, just because it has a junction potential. You don't.
Hmm.
What you do actually is you allow that junction potential to be there, and now you play with the device. This device is actually the diode, called as a diode. Okay, so
Yeah.
first let me
Okay.
give you
Hmm.
the definition exactly, right? So now, even if you don't recall, you may be recalling words like junction potential, right? So the junction potential.
Hmm. Yes. Yeah.
Okay. I will just give you a quick overview of. So this is what we had studied, just for your quick reminder, because I know it was not available to you to have a relook. Okay. So diode is basically a nothing but a PN junction device. So we allow the PN junction to get created,
Hmm.
which happens naturally.
Hmm.
And how does it happen? You bring P-type and N-type materials, you bring them together, and the free electrons from the N region diffuse into P region, and holes
Yeah.
from the P region diffuse into N region,
N region.
right? So they cancel each other and results in a depletion region. And in the
Yeah.
depletion region, you still have immobile ions, which is arsenic ion or boron ion, right? Depending on is it
Yeah.
N or the P. This results in the electric field is there between a positive charge to negative charge, which is ions. And this electric field then creates a junction potential, also known as barrier potential or a built-in potential.
Hmm.
So, which is a potential difference across the p-n junction at equilibrium. So, right now, what you've done is you've allowed a p-n junction to get created, and it is in equilibrium. So, after a while, the diffusion stops, and the hole and electrons stop moving from each other because they start getting a repelling force from the ion itself. Right.
Yeah.
So finally, the equilibrium is attained and nothing will move. An electric field will get created and a junction potential will exist. That's
Hmm.
it. Now, but you have to finally see this PN junction is good for nothing. We have to use it. Okay. Now, when you put it to use the PN junction, it actually is a diode. Okay. This device, which is a PN junction semiconductor device, is known as a diode. Diode. Okay.
Yeah. Okay.
Now, okay, so let's see the context of it. Now, what is the role of junction potential in a diode? We already know the junction potential will oppose the further movement of charge carriers, which are
Hmm.
electrons and holes. It will not allow, right? And finally, junction potential will result in an equilibrium and a very stable depletion region. The
Hmm.
width of the depletion region will be fixed. There will be equilibrium, ions on both the sides, no further movement, right?
Yeah.
Now, what you do is you apply a forward bias, which means you connect an external voltage and say, I will overcome this junction potential. I will break it. Okay.
Hmm.
For example, you created a diode with the help of silicon. Okay.
Okay.
And junction potential will be around 0.7 volt. So silicon is created N-type with the help of pentavalent impurity,
Hmm.
P-type with the help of a trivalent
Yeah.
impurity. And then you join them. When you join the two sides, it results in creation of a junction potential, which is of the order of 0.7 volt
Hmm. Yeah. Okay.
or silicon diodes. Okay. Now what you do is you apply the P side of this diode to the
Hmm.
positive terminal of the battery
Yes.
and the inside of the diode to the negative terminal of the battery, which
Yeah.
means earlier you just had a junction potential inside the diode, which was created naturally in factory.
Hmm. Yeah.
Now you're applying an external voltage also. Why are you applying external voltage in this manner? So that you can reduce the width of the depletion region. You want the current to flow through the diode.
Hmm.
But inside the diode, what you have is a equilibrium and a junction potential. So somebody will have to break this gate of potential. So therefore, to break that barrier inside, you apply a reverse voltage in the direction reverse of the internal electric field or the barrier potential to break it. And that is done with the help of the battery. So battery sees that inside there is a gate of 0.7 volts.
Hmm.
A battery then provides a voltage of 1 volt.
Okay.
So 0.7 volt gets neutralized and the balance 0.3 volt is used for flow of current.
Current. Yeah.
So equilibrium is lost. There is no more
Hmm.
equilibrium. Okay, because you have started up. So the depletion region becomes narrower and narrower. Now you have
Yeah.
force coming in, which will let the electrons move to the hole side, and the hole will be moving towards the N side because you're applying external potential to overcome the junction potential.
Hmm.
This particular strategy of applying uh, potential to overcome the junction potential and allow for the free flow of current is called as forward bias mode.
Okay.
But if you say, I will increase the size of the depletion region so
Mm.
that hardly any current can flow through it, which means I will increase the resistance inside.
Mm.
Whatever junction potential is there, I will help it and I will increase the junction potential further. Further, already there is a 0.7 volt junction potential in silicon-based PN junction diodes. I will increase it further. So what you do is you connect the P side to the negative terminal of the battery and N side to
With
the
the
positive
positive.
terminal of the battery. What does it do? It becomes friends with the junction potential inside. So thus it further aids it and the
Mm.
depletion region further widens.
Okay.
This behavior is called as reverse bias behavior. Now, if you use such a diode in practical usage, the use practically will be that in that area where the current will come, the current will not be able to pass it. So sometimes in electronics applications, in mobiles and all that, you need certain diodes which don't allow current to flow in
Mm.
some areas of the circuit. There we don't use resistors. We use the diodes to stop the flow of current because the
Yeah.
current we're dealing with is in milliampere, very, very small.
Mm.
Okay. So, and the behavior which is shown by the diode, which we will study later, is very different from the resistance. Resistances follow Ohm's law. The diodes don't follow Ohm's law. Although they sound like resistance in the case of reverse bias, that they are further increasing the junction potential, widening the depletion region, and reducing the current flow, which is what generally a resistance does, right? Resistance also
Mm.
reduces current. But diode reduces the current in a different manner. It reduces the current by increasing the size of the potential, not by offering resistance to the flow of electrons of the metal. It does not. It offers higher depletion region or a junction potential increases. So the mechanism by which a normal resistor reduces current and the mechanism by which a normal uh, diode reduces the current, they are different. One is using the increase in junction potential called as reverse biasing to reduce the current flow. But metals, the resistors don't work that way. They have nothing called as a junction potential inside them. They
Yeah.
have material which the electrons collide with and lose energy, and we say that this material is offering resistance. But in the case of reverse bias of a diode, there is nothing like that. You have junction potential being increased to reduce the current flow. Okay.
Yeah.
So you will use the diode in two ways. So you will have a PN based semiconductor diode. You will say, okay, good, you have provided me 0.7 volt of junction potential inside it in an equilibrium position. No current is flowing, but I want to use it. So, okay, use it. So there are two ways you will be able to use this. One is the forward bias, which will allow the current to flow it.
Mm.
The other method is the reverse bias, which will not allow any current to pass through it.
Yeah. Okay.
Both of them actually are doing reverse work. In the forward bias, you break the junction potential, but in the case of reverse bias, you increase the junction potential by using external battery in both the cases,
Okay.
right? So current flows in forward bias, current doesn't flow in reverse bias.
Reverse biased. Yeah.
Okay. Now, one of the applications of this junction potential, which is used in industry, which we will study also, is basically called as rectification. If you see the syllabus, we have to do junction diode as a rectifier.
Yeah.
We are not studying rectifier right now. Wait for it. But
Mm.
just for knowledge, rectifier, what it does is if you provide it AC, which is a
Yeah.
sine curve, alternating current like this,
Mm.
it will cut off the negative part and only positive parts will be there. So it
Okay.
converts AC into DC, only one direction. Okay, so
Rectifier.
it's called rectifier. So if you have a graph which looks like a sine graph,
Mm.
remove the negative part of the sine graph, that is the final voltage you will have. And this type of voltage, which is a rectified voltage now, okay?
Mm.
So you generally see this in alternating current, where you see RLC circuit, right? This is a voltage.
Yes.
Voltage and time or omega जो भी दिया है. Now what you do is you apply a alternating source. Okay, so this is your diode. Okay, the triangle in the line. This is the diode. Triangle is always the positive side. What you do is you connect it to an alternating source. Now, alternating source is not a battery. It becomes plus and then minus, minus, plus, right? It keeps on changing. It is
Yes.
plus and minus. In 1 second, it becomes 50 times positive and 50
And
times.
50 times negative.
If you apply this device, then 50 times it will become forward biased and
And
50 times it will become negative biased.
okay.
So during the negative bias, during the positive bias, you will see current through the
Yeah.
diode. But during the negative bias, it will not allow any current. So you will get
बस हाँ ये ऊपर वाला.
this is negative, na? So this is getting negatively biased. So negative and positive. So then negative part is connecting to P and positive part is connecting to the negative part. So this part is the reverse bias. In reverse bias, no current is observed and therefore you see this blank space, right? So this is your blank space. You don't see any current. So this is the P, positive. Right? So you only see the part of the current which is the forward biased diode. So this diode, PN diode, gets forward biased in the positive part of the cycle and gets reverse biased in the negative part of the cycle. And therefore, you see this type of graph as an output. Such a voltage, which you're noting, current or the voltage, which you're noting across a diode is called as a rectified form, which means it is converted into only positive. So it becomes kind of DC, direct current. Direct current, though, from the battery is not fluctuating, it is stable like this, right? 5 volts. But since this is continuously changing over time, but it is in positive direction only, we can still call it DC. Now, normally DC looks like this. It doesn't change with time when you have battery. It's a straight line, 5 volt. But this may go up to 5 volt, may reduce. Again, 5 volt may reduce. So this is called a rectified. So now we are using diode as a rectifier.
Okay.
Okay. We will study this, how exactly we do this, but quick review of forward bias and the reverse bias is important. Okay. Now what we do is, now because we have connected them in a forward bias and a reverse bias, we will study how the change in voltage in forward bias will result in change in current. A lot of people expect that the behavior will be identical to a resistor, straight line. Increase in voltage should result in increase in current. You keep on increasing the voltage, the current will keep on increasing in the case of a resistor, right? You will get a straight line at an angle, right? And if you see the Ohm's law, it is V is equal to IR. So V is equal to IR. If you have to draw a VI characteristic of a resistor, it looks like this, where the slope is theta, the tan theta is equal to V by I, but V by I is equal to R. V by I, right? So the slope of a VI graph gives you the resistor, the value of the resistor in a circuit. It's a straight line, you can see, right? Directly proportional. R is fixed. Keep on increasing the voltage, the current will linearly increase.
Yeah, okay.
Got it? So but this is not the behavior you will get in diodes. They don't show straight line. And they have something very typical. In diodes, what you have to do is you don't draw the graphs which are VI graphs. What you draw instead is a graph which is IV graph, which means your y-axis will be I and your voltage will be here. So it's reversed. This is the way you draw the IV characteristic. Therefore, the word IV characteristic. If you see the word VI characteristic, then V is in y-axis and this is in x-axis. But if you see IV, then this is in y-axis and this is x-axis.
Yeah.
Okay. So what we have to do, we have to understand the graph of a diode, PN junction diode, when it is forward biased. And what you're doing is you're increasing the external voltage of the battery gradually like this. And then we will see what happens to the current. Various readings of the current will be taken. And we will see what type of graph do we get. Here we will say it is forward bias because you're applying a positive voltage, right? And when you start reversing the voltage to reduce the current flow, which means you start becoming friends of the junction potential and further increase the resistance to the flow of current. You will see this area is the negative potential. So when you draw the IV characteristic of a PN junction diode, I is always in the y-axis. This side, which is a positive x-axis, is forward bias, and the negative axis is the reverse bias. So this is your reverse bias.
Yeah, okay.
Okay. So we will understand now the characteristics, how the graphs appear to be in the case of. So what we'll do is we will apply a voltage. We will note the corresponding current. Then we will slightly increase the voltage. Then we will note the current. And we keep on doing this. We take many readings. And this experiment is probably in the syllabus also. So a lot of readings are taken. You keep on increasing the forward bias. And what you find is that after a certain level, the current stops increasing.
Okay.
So let me just show you the graph, what exactly happens. Or you don't need any further voltage to increase the current because that is the highest. This is the way the graph looks like. So first of all, you have to remember that one side is in milliampere. Remember, we're not dealing with 5 ampere, 2 ampere. We're dealing with milliampere. We're dealing with electronics. Electronics current, like you use adapter with a mobile. The kind of voltage you give to a mobile is not 220 volt. The adapter reduces the voltage to very small number of volts, 4 volt, 3 volt. And the current inside the mobile phone is to the tune of this. And in fact, in the laptops also. Milliampere. Okay. So you are increasing the voltage and taking readings. You have made the voltage here like this, right? This is your voltage. This is the reading. Then you slightly increase the voltage. Then this is the reading you're getting, right, for this particular one. So this is your voltage. This is your current. So you join all the dots. You have to memorize this graph. Also remember that you're drawing a milliampere versus voltage. So milliampere is measured with the help of ammeter, a very fine sensitivity, and the voltage is measured with the help of voltmeter.
Okay, yeah.
And so this is a forward bias, what you see in front of you. Forward bias, okay? Now, why this behavior we will study. Okay, why this behavior, why the graph looks like this. So you can be certain that the graph doesn't look like a straight line. It's a curve. Now see what happens when you do the reverse bias, which is go on the negative x-axis. Something will happen. The graph looks very similar, but now it is in the third quadrant. Now, however, the current value is microampere, which is negligible current, by the way. Hardly any current. This current is actually known as leakage current. We will study. Then you see, this is a reverse bias. The current is there, but the value is small. And finally, after a certain voltage, the current stops increasing. Sorry, after a certain voltage, the current plateaus to a certain value. So at a certain value of voltage, you don't need to increase the voltage to get any more current.
Yeah.
And you can see the voltage has attained the highest possible value, and you can see the current actually is going towards a very large current. Although it is very small, it is microamperes, not even milli, which is good current. So if you see a milliampere current graph generally like this, you can be very sure that they're referring to a reversed biased diode. But if you see a milliampere graph, microampere graph is reverse bias, but if you see a milliampere graph, it is most certainly a forward bias. And the first quadrant is always the forward bias, and this particular one is the reverse bias.
Reverse bias.
Very small current. Okay, now let's see the behavior. What happens? You can see in the case of the forward bias, I'm increasing the size of the graph, okay, so that you can see. What you will see is that the initial increase in voltage increases the current drastically. The current is continuously increasing with the help
Yes.
of increasing forward bias, right?
Hmm.
You can see the, it is increasing,
Yeah.
right, with a certain voltage, and then let's see. Sorry, the behavior is that initially the growth is slow, right? So if you have this much voltage, you only get this much current. Now you have this much voltage, you're getting this much current, sorry, this much. But if you have the same increase in the voltage, the current now increases, the slope is increasing, right?
Yeah.
The slope is increasing. Here, the slope is only this much, right? Here, the slope is more, if you notice. So the rate at which the current is increasing in the later parts of the graph is very high. Here, the current raise is very, very high, right? The slope is increasing,
Yes.
right? So, but in the initial phase, the current is not increasing at a good speed. It's very slow in this part, especially.
Hmm.
And now the slope is boom. And now here it is more. A very small increase in voltage here has increased the current drastically, right?
Yes, sir.
Okay. Okay. Let's see why this behavior. What exactly is happening inside the diode when it comes to forward bias and reverse bias.
Hmm.
So if I ask you, what is the purpose of drawing the IV characteristic of a PN junction diode, what will you say? Why do we draw this graph? Because we
It
want to see how
shows
the
the
current flows
current harm, like
when the
how
voltage
it's
is
changing.
applied,
Yeah.
right? How it varies with the applied voltage.
Yeah.
One, forward bias, second, reverse
And
bias.
reverse biased.
Okay. So the applied voltage, uh, which is so if your applied voltage is less than the threshold voltage, which is zero
Yeah.
point 0.7 volt, which is
Hmm.
the inbuilt potential inside the diode.
Yes.
Silicon-based diodes, PN junction diodes,
Hmm.
have zero point 0.7 volt. And
Yeah.
if you make the PN junction diode with the help of germanium as a base and then do doping,
Hmm.
impurity addition, the threshold voltage or the inbuilt voltage, which gets created called as a barrier potential, is zero
Hmm.
point 0.3. So for
Okay.
germanium, the natural junction potential is 0.3, and for
Hmm.
silicon, it is 0.7, right? And if you apply a voltage which is less than 0.7 for silicon-based PN junction diode and less than 0.3 volt for germanium-based diodes, you will not see current inside the
Current. Yeah.
diode. No current, because you're not able to break the barrier.
Yes.
But, but
When it is
if
higher than the.
if you go beyond the threshold
Uh,
voltage is also called as a cut-in voltage.
hmm.
Cut in, CUTIN, cut in.
Yeah.
Okay, so you will see exponential increase in the voltage.
Current. Voltage. Yes. Okay.
Sorry, current is exponentially increased with the help of
Hmm.
voltage. Yes.
Voltage. Yeah.
What is the equation which is applicable to find the current in a junction diode in a forward bias? Okay, this is the equation. So the rapid initial is slow and then rapidly increases the
Hmm.
current in forward bias. We say it's exponential increase, and this is the way we define it. See it very carefully. This is the external voltage you have applied with the help of battery, the forward biased battery, which is helping it forward bias. This is the
Yeah.
current, right? So note the quantities. charge of electron, Q. Applied voltage, V. Boltzmann constant, which you study in kinetic theory of gases in class 11th.
Yeah.
Temperature.
And yeah.
And note one more thing. What is a reverse saturation current?
Hmm.
This is reverse saturation current. I'll tell you what it is. It's a leakage current and reverse bias. But anyway, first of all, note the keywords.
Yeah.
Exponentially, it increases. And the equation which decides the current is not Ohm's law. There is no Ohm's law applied to diodes. It's a very different type of equation. Okay. Now, let's talk about the behavior in the reverse bias. So, in the reverse bias, the applied voltage widens the depletion region,
Yeah.
increases the junction potential,
Hmm.
and starts acting as a stronger barrier to current flow.
Okay. Hmm.
Right? But a small reverse saturation flow current is still observed. You're trying to increase the junction potential by giving reverse bias. But there is still a current that flows. It is called as a reverse saturation current. And this current is not because of the majority carriers, which are, electron moving towards the P side, the hole moving towards the N side. That you're able to stop. But this is because of the N side. The N side has some holes in it, and the P side has some electrons in it. And therefore, they are minority carriers.
Hmm.
P side, majority is hole. The minority is electrons. And
Yeah.
on the N side, you have the majority as electrons, but minority as holes. Now, the current flow, which is a reverse saturation current flow, is because of the minority carrier,
Okay.
which is not impacted by the
Hmm.
junction potential.
Yeah.
For them, it is good if there is a reverse bias. They say, okay, we are not electrons or holes, we are minority here. So we can flow across this. Okay, so minority current carriers result in a reverse saturation current.
Okay.
Okay, it's a very small current. Anyway, we have seen that it is in milliamperes. So in reverse bias, we saw milliampere current. That was nothing but the reverse saturation current.
Yeah.
Reverse saturation current is due to the minority carriers, not due to majority. All right. Okay, now let's talk. We have emphasized that current increases exponentially. There is, even if you have reverse bias, still some current flows across the diode. This current is basically the reverse saturation current.
Hmm.
It is very small in the reverse bias. We are not able to bring the current to zero even in reverse bias. We have small due to minority carriers. Some current flows in the opposite direction to the natural flow. The natural flow is N to P and P to N.
Yeah.
But in the case of reverse, it is not natural. It is holes are moving from N side to the P side, and electrons are moving from P side to N side. Very, very different, right? So we have emphasized current flow, right? Now let's emphasize the what is happening on the voltage front, why that voltage, etc., right?
Okay.
Now let's look into the behavior of the reverse bias. Okay, go to the reverse biased graph. Okay, I will just bring it up. So first, let's study what is happening on the reverse bias side. Do you see that after a while, after a certain voltage, the voltage is not increasing, but the current is increasing?
Yeah.
Or reverse bias is being applied, but the current is continuously increasing, right?
Yes.
This region where you see a sudden increase in the current, right, is called as the avalanche breakdown.
Okay.
Avalanche breakdown. Because now what you're doing is you're applying so much energy with the help of the reverse bias.
Sudden
that
increase.
The carriers which get so much energy because of the increase in the voltage continuously.
Yeah.
That they're able to cross over to the junction potential. And again, minority carriers. Carriers are minority, but you have increased their energy to so much level, such a level that now they are able to more number of minority carriers start increasing.
Yeah.
And therefore, we call this as a avalanche. Avalanche is like if you see snow coming from mountains, call it avalanche. Like a lot of snow gets collected, small snow, and a lot of snow is makes appearance and creates havoc. So that is called avalanche.
Yeah.
You must have seen in mountains, snow is coming down, right?
Understood. Yeah.
So something very similar happens, that you are increasing the voltage and reverse bias to such large extents that the number of minority carriers increases drastically. And there is an avalanche breakdown.
Yeah.
Okay? And there is so this particular region of reverse bias where there is no increase in the voltage, but you see sudden increase in the current, like a straight line almost going down, right? This region is called, that particular voltage where it starts happening is called as a breakdown voltage.
Yeah.
This voltage, right? So you can see this voltage is your breakdown voltage.
Avalanche region.
Yeah.
Okay.
And this current which you get, which is going vertically down infinitely, this current is called as a avalanche current.
Okay.
Okay. And there is another term which you have to learn. It is called as a Zener breakdown.
Isn't can you repeat कौन सा breakdown?
Zener.
Zener. अच्छा ठीक है.
Right. So one is, the current is increasing sharply because you have crossed the threshold voltage, the breakdown voltage, sorry, right? So breakdown voltage has been reached because you have applied a very high value of reverse voltage. The reverse voltage is very high, and it crosses the breakdown voltage, right? And because of the breakdown, I will tell you the meaning of the word breakdown. Okay, now that behavior of the PN junction to stop the current flow is no longer there because you have applied so much reverse bias that minority carriers start going in large quantities to the other side. Practically, what it means is that the current has come suddenly from somewhere because of very high value of reverse bias.
Okay.
Current is obviously because of minority. If you don't apply very high reverse voltage, you get a saturation current. It's very small.
Yeah.
But if you keep on increasing the reverse voltage, then the number of minority carriers increases drastically. And you will start seeing some observable current, although in milliampere again. This current will be still in milliampere, but we will say that it's still an avalanche. That means you have actually changed the behavior of the PN junction diode in a reverse bias. You expected very small current, which is saturation current, the reverse leakage current, but now you're seeing some current in it. So we say change its behavior.
Okay.
Okay. But what happens is, if you use a diode in this manner, because of the increase in current, the diode gets damaged. You can't use a diode in reverse bias with very high voltages. It gets damaged.
Okay.
So somebody said, then how do we use it in circuits if it gets damaged, right? So what you do is you apply a reverse bias in certain limit.
Yeah.
You don't go beyond the breakdown voltage, which breaks the behavior of the reverse biased PN junction diode too much, but you keep it in control. If you do that, then this diode can be used in the practical applications. Then this diode is known as the Zener diode.
Acha, okay.
So then, instead of depending on avalanche breakdown, which is uncontrolled, you control the breakdown so that you don't damage the diode in that process of avalanche breakdown, and you restrict that breakdown to a new breakdown called as a Zener breakdown.
Okay.
Zener, Zener, which is a low breakdown voltage.
Okay.
If you keep the diode in reverse bias within the limits of the low breakdown voltage, you're still breaking it, spoiling it, altering its behavior, still getting a rush of minority carriers,
Yeah.
but within the limit so that you don't damage it. Such a diode is called as a Zener diode,
Okay.
right?
Hmm.
This is the way you will use so somebody says, how will you use a reverse biased PN junction diode? It's a complete flop, because if you cross the breakdown voltage drastically, that means there is
Yeah.
a breakdown voltage. Now the behavior will start changing because you're breaking it down. Now you will
Yeah.
see increase in current, that vertical straight, right? But this is going to finally spoil the diode. How will you use so how do you use a avalanche breakdown? I will say I will not use avalanche breakdown. I will control the avalanche breakdown to a certain lower level of breakdown voltage, and then I will use it in operations. Such a voltage in which you control the avalanche breakdown to a restricted value without spoiling, so that you don't end up spoiling the PN junction diode, is called as a Zener breakdown.
Zener.
It's a controlled avalanche breakdown. Okay?
Yeah.
So we are saying that a diode has to be protected,
Okay.
right? You have to design it for the breakdown operation. And the way to design this is to have some mechanisms in place to create a Zener breakdown voltage instead of a avalanche. Avalanche is going to kill the diode.
Yeah. Okay.
You have to do something to convert it into a Zener breakdown.
Yes.
Right. So in reverse bias, you have a lot of stories to write. So if you say, so one is your forward bias, where you see exponential increase in the current in microamperes, initially slow,
Yeah.
very fast, and then very fast. The second part of the IV characteristic, where we are
Yeah.
studying the behavior of the current with respect to the changing voltage,
Hmm.
is the reverse bias part, the negative side, the third quadrant.
Yeah.
In that, you notice, okay, for a certain voltage, you have a reverse saturation current of milliamperes. You reach a breakdown voltage.
Okay.
And if you go beyond breakdown voltage, you will see a rapid increase in the current, like straight line almost, because the diode has broken down,
Yeah.
right?
Yes.
So in the reverse bias, you see negligible current till the breakdown voltage, and after the breakdown voltage,
Yes.
you see a sharp increase in the current.
Current.
थोड़ा समझ में आ रहा है?
Yeah.
सिंपल भाषा में बोल रहा हूँ मैं, very simple. Avalanche, these words, etc., etc. Okay.
Yeah.
Okay. So let's get into some more details, slides more detail. If they ask you what is avalanche breakdown, right? What will you write? You should have some words also, right?
Yeah.
Obviously, avalanche breakdown has everything to do with uncontrolled reverse bias of a PN junction.
Yeah.
Avalanche breakdown actually increases the minority carriers drastically, which start flowing across the junction. Although junction is very, very powerful, it doesn't allow majority carriers to flow, but it allows the minor, it cannot oppose minority, right? It can oppose a positive side can oppose the flow of whole from the other side. A negative ion wall, a wall which is made up of arsenic ions, which are negative, positive, can block the flow of holes from the other side. And similarly, boron which is negatively charged,
Hmm.
acceptor ion, will not allow any electrons to come through it.
Yeah.
But a positively charged arsenic ion
Hmm.
cannot prevent the flow of holes from the other side. Holes
Yes.
are positive, arsenic side is negative. So, but there are very limited minority carriers. But if you go beyond the breakdown, then you will see a noticeable increase in the current because the minority carriers start collecting inside on the other side and start moving towards the other side.
Okay. Yeah.
Read this.
Avalanche breakdown is a phenomenon that occurs in semiconductor devices such as p-n junction diode. When the reverse bias voltage exceeds a critical value called the breakdown voltage. At this point, the current through the diode increases dramatically due to the chain reaction of the carriers.
Carriers are minority.
Yeah. High reverse bias voltage and a reverse voltage is applied across a p-n junction. It widens the depletion region and strengthens the electric field across the junction. If the reverse voltage exceeds the breakdown voltage, the electric field becomes strong enough to accelerate the minority charge carriers to a high velocities. Yeah.
Right?
Hmm.
Okay, read further. This is the exact mechanism. This is too much for detail. Even if you can remember what you have just studied,
Yeah.
it is more than enough for you. But you can write many things if you want to, right? These are slightly more details, but it will give you very good insight what happens in a exactly is happening. Read.
The high energy carrier.
So these minority carriers, what they do is they reach the other side. They collide with the crystal lattice of the semiconductor material,
Yeah.
right? So these collisions dislodge bound electrons from their atoms, creating additional free electrons and holes. Right? So what happens? So the electron which is on the p side, it is moving,
Yeah.
right? In the p side,
Hmm.
it collides with the boron atoms
Hmm.
because p side is boron, right? A boron impurity.
Hmm.
Silicon added with boron, dopant, p
Hmm.
side, right? P side, p type semiconductor is on the sorry, left hand side. Electrons will get dislodged on the left hand side. P side generally is rich in holes.
Yeah.
But the minority carriers are there, electrons. Very few electrons are there. But because you have few electrons accelerating, they will collide with boron and dislodge the electrons. So you will start getting more electrons on the p side. The number of minority charge carriers also increases. For current to increase, you need more minority carriers, right?
Yes.
That means there were few electrons already available. Now you want more electrons to be available on p side, which is generally rich in holes. Who will give those electrons, extra electron? The atoms on this side, on
Okay.
the p side, will give you the extra electrons. Because now the very few electrons which you already had as minority carriers start accelerating and colliding with the atoms in the crystal lattice and dislodge. That means remove the electrons from them, thereby increasing the number of electrons on the p side.
Yeah.
P side generally doesn't have any electrons, very
Mm.
few. But here you have electrons. Right? So
Okay.
if you want additional free electrons, how will you get them? By colliding
Yes.
and dislodging the bound electrons. जो electrons bond में है उनको हटा देंगे. Minority carriers. और इलेक्ट्रॉन अपने साथ लेके चलेंगे दूसरी साइड पे. तो वो सडन इंक्रीज इन द करंट जो है, बर्फ जो इकट्ठी होती जाती है, वो नीचे जब उतरती है तो अपने साथ और बर्फ को इकट्ठी करती है. तो वो बर्फ का गोला बन जाता है फाइनली.
Okay. Yeah.
दिस इज व्हाट हैपेंस हियर आल्सो. 6 इलेक्ट्रॉन आएंगे और टक्कर भी मारेंगे, उस साइड भी जाएंगे और साथ में 6 को और ले जाएंगे अपने साथ. करंट बढ़ जाएगा. जो नए इलेक्ट्रॉन जनरेट हुए वो भी एक्सेलरेट हो गए.
हाँ. और जो
उन्होंने भी टक्कर मारी, वो औरों को निकाल दिया उन्होंने. उस साइड खुद भी चले गए और खुद निकाल के भी चले गए. चेन रिएक्शन का काम कर रहे हैं. तो what is happening? The carriers are getting multiplied.
Yes. हाँ.
Look at this. So this process is called as impact ionization. You don't need to know these words. You can just write what is happening. Electric field is increasing. The high energy carriers, which are minority carriers, collide with the atoms, dislodge the
Yeah.
electron. And on the p side, minority is electron. And on the n side, the minority is hole.
Whole, okay, yeah.
And reverse is happening on the, and just right, and reverse is happening on the n side. So say so one is obviously the, once you attain the breakdown voltage, now you have very strong electric field available. This strong electric field pushes the already existing minority carriers to the other side. And once this strong electric field, which you are provided with the help of reverse biasing, provides energy to the minority carriers, these minority carriers on the p side start dislodging more minority carriers, which are electrons. And this results in a chain reaction of more electrons getting generated and jumping to the other side.
Yeah, okay.
This is called as impact ionization or carrier multiplication. See what carrier multiplication is doing. Read this. Last paragraph.
This process of impact ionization repeats, leading to an avalanche-like multiplication of charge carriers. The result is rapid, uncontrolled increase in the current through the diode. Yeah, okay.
Correct. तो बर्फ का गोला कैसे बड़ा हो रहा है?
ब्रेकडाउन ज्यादा हो रही है, प्लस
Yes.
रैपिड हो रहा है.
आपने
और
ब्रेकडाउन वोल्टेज लगाई है, वो ब्रेकडाउन वोल्टेज इतनी बड़ी हो गई है कि उसने बहुत बड़ा इलेक्ट्रिक फील्ड बना दिया. वो इलेक्ट्रिक फील्ड अब माइनॉरिटी कैरियर्स के ऊपर एक्ट कर रहा है. माइनॉरिटी कैरियर्स एक्सेलरेट होने लग गए. जब वो एक्सेलरेट हुए तो उस रास्ते में एटम्स मिले, उनके इलेक्ट्रॉन्स जो थे बॉन्ड में, उनको हटाया उन्होंने, अपने साथ ले गए, और जो इलेक्ट्रॉन नए निकले उन्होंने फर्दर कोलिजन्स करे और इलेक्ट्रॉन निकाले. तो नंबर ऑफ माइनॉरिटी चार्ज कैरियर बहुत ड्रास्टिकली बढ़ी है.
ठीक है.
So avalanche breakdown is basically voltage driven phenomena. The reverse bias voltage controls the avalanche breakdown. Uncontrolled. If you read the last line, what is happening? बर्फ भी uncontrolled ही गिरती है, right? There is no control, right? So you can see the uncontrolled. रहेगा मिली एम्पियर में, लेकिन अगर सैचुरेशन करंट 2 मिली एम्पियर था, तो ये 20 हो जाएगा. पहले से तो 10 गुना हो गया ना.
Yes.
जो 10 टाइम्स देखेगा वो तो हैरान हो जाएगा. 10 टाइम्स कैसे हो गया? ऐसे हुआ. पढ़ो इसको.
It occurs when the reverse voltage exceeds the breakdown voltage, which depends on the material properties and
breakdown voltage of breakdown voltage जो होती है, how do you decide it? Basically जो डोपिंग होती है, जैसे बोरोन और आर्सेनिक होती है, right, उससे डिसाइड होती है ब्रेकडाउन वोल्टेज कि कितनी जल्दी वो ब्रेकडाउन कर जाएगा. Right? It is decided by the doping levels and material property. जैसे मैंने आपको बोला, silicon has a 0.7 breakdown voltage. Germanium has 0.3 breakdown voltage, but it is not only dependent on material property, it also depends on the doping level. आपने कितनी impurity उसमें ऐड करी हुई है, उससे भी डिसाइड होता है. अब देखो, ये तो हो गई destructive वाली, right? You will destroy the whole stuff. Read this now.
If the diode is designed to handle the high current, the process is not destructive. However, if the current is not limited, the excessive heat generated can damage the device. Yeah, okay.
You don't want destruction of the diode itself. So you have to control it, right? You have to find a way. How do I control this? Right? So you design a special purpose diode called as a Zener diode. So Zener diode is a special type of diode which only works in a reverse breakdown.
Yeah.
It doesn't work in forward. If you see the word Zener, okay, reverse avalanche uncontrolled था, और मेरे को इसको control करना है. Okay, I'm going to do something about it, and I'm going to create a Zener diode.
Yeah.
Okay. Now they may ask you a question. What is the difference between avalanche breakdown and a Zener breakdown? What will you write?
avalanche breakdown is like when the मतलब जब ज्यादा हो जाता है तब avalanche होता है, like when there's a drastic change in the current, and when Zener is like जब dip.
Read it. So first of all, I told you the breakdown voltage is dependent on doping. And you have
हाँ
to
वो
do
तो है ही.
something to convert a normal diode, which shows avalanche breakdown, into a Zener breakdown situation. You have to do something, right?
Yeah.
What is that something? That something is that generally a normal diode exhibits the stuff like light doping, and the depletion region is very wide.
Yeah.
But you want special control on this. Otherwise, it will get destroyed. What you
Yes.
do is you design it in such a way that it, first of all, increase the doping.
Doping heavy हो जाती है.
करो ज्यादा. और डिप्लीशन रीजन क्या होता है? डोपिंग बढ़ाने से कम हो जाता है.
Okay.
नैरो कर देते हो आप उसको. It becomes narrower. Right?
Yes.
Now, the avalanche breakdown is mainly driven by impact ionization and high electric field. Yes, we know this. This uncontrolled multiplication, snow-like effect. But the Zener breakdown is not controlled by this high electric field and impact. It is controlled by something called as a quantum mechanical tunneling of electrons. You will have to memorize this word.
Okay.
You can get a 2 marker, right? Or 3 marker. Or a MCQ or a reasoning assertion, something like that on this topic. Avalanche versus Zener breakdown.
Zener breakdown, okay.
Where does it happen? It happens at high reverse voltage. We know that. But this happens that you don't want it to be taken at a value where the current increases infinitely. You want to keep the breakdown voltage also limited in Zener.
Yeah, okay.
Right? They can ask you avalanche versus this situation. So if it's a 1 marker question, okay, give reasoning. So give a difference between avalanche and Zener breakdown. Okay. What situation? How will you 1 marker if they ask you a 1 marker? Obviously, you will need to read it yourself, memorize all of this to get hang of what first time. Look, what is this?
Avalanche breakdown is a critical concept in understanding the behavior of diodes under high reverse bias conditions.
But it cannot be used for practical purposes. So therefore, we design the device such a way that you have regulated voltage. The reverse breakdown voltage is regulated. And you also want to provide circuit protection. And you don't want the circuit to get destroyed.
Yeah.
And device should not spoil. So you want to control the voltage. You don't want very high reverse voltage. You want device not to get spoiled.
Yeah.
Then you use a Zener breakdown, not avalanche.
Okay.
Right? They ask you these questions. What is an avalanche breakdown? What is a Zener breakdown?
Zener breakdown.
They will ask you.
Yeah, okay.
You memorize it. Listen to me. Listen it again. Memorize it. You have to just verbatim go and repeat it. Don't put any extra effort. If you memorize all of this, you can write better than most of the students.
Yeah, okay.
Okay. So they say, okay, now what you have to do is explain the Zener breakdown voltage. Explain, which means whatever you know about Zener breakdown voltage, and they said draw a graph. What will you write? Start with this.
Zener breakdown is a phenomenon that occurs in the p-n junction diagram when the reverse bias applied exceeds the critical value called the Zener voltage. Unlike the avalanche breakdown, Zener breakdown is caused by the quantum mechanics.
Quantum. I told you to memorize this.
Quantum
I'm not
mechanics.
explaining you this. This is beyond your understanding. Okay. Quantum mechanical tunneling. It's a very chhod do ab isko. Memorize it. पढ़ लिया?
हाँ
ठीक है,
जी, yes, समझ
तो
गई।
एक तो आपने समझाया व्हाट इज जीनर ब्रेकडाउन, ये समझा दिया आपने पहला पैराग्राफ में।
हाँ,
अगले अगले में क्या समझाओगे कि होता
जेनर
कैसे है?
वोल्टेज।
होता कैसे है, क्या करते हो, इसको कैसे अचीव कर पाते हो, अवलांचे से जीनर पे कैसे आते हो, राइट? मैकेनिज्म क्या, देखो
हम्म।
सब कुछ लिखना है ना।
हाँ, एक से हाँ पढ़ रही हूँ।
पहले तो मैन्युफैक्चरिंग पे जाओ इसकी।
हाँ, heavily doped p-n junction, thin depletion region, allows strong electric field.
इलेक्ट्रिक फील्ड इसमें भी स्ट्रांग है, जैसे
हाँ।
कि अवलांचे में था, लेकिन वहां पे
हम्म।
जो वोल्टेज लगाई थी बहुत ज्यादा थी। या
हम्म।
छोटी वोल्टेज में ही भी हासिल कर सकते हो आप।
यस।
इलेक्ट्रिक फील्ड तो चाहिए इलेक्ट्रॉन्स मूव करने के लिए, मतलब माइनॉरिटी कैरियर्स को मूव करने के लिए एक साइड से दूसरी साइड इलेक्ट्रिक फील्ड तो चाहिए। बट प्रॉब्लम ये होती है कि
हम्म।
अगर आप नॉर्मल केस में इलेक्ट्रिक फील्ड हाई करते हो तो आपको पोटेंशियल बहुत ज्यादा लगाना पड़ता है, क्योंकि
हम्म।
जंक्शन बहुत वाइड होता है। मतलब डीएक्स इज वेरी हाई जनरली, जो जंक्शन की विड्थ
या।
होती है वो बहुत हाई होती है, डीएक्स।
हम्म।
इलेक्ट्रिक फील्ड होता है माइनस डीवी बाई डीएक्स, ये बहुत हाई है। इलेक्ट्रिक फील्ड भी बहुत हाई है, तो
यस।
वोल्टेज डिफरेंस बहुत हाई हो जाता है।
हाँ।
वोल्टेज डिफरेंस बहुत हाई हो जाता है तो वो ब्रेकडाउन वोल्टेज को क्रॉस कर देता है बहुत ज्यादा, और अनकंट्रोल्ड करंट आ जाता है, अवलांचे ब्रेकडाउन हो जाता है, क्योंकि वोल्टेज ब्रेकडाउन से बहुत ज्यादा कर दिया आपने।
या। ओके।
क्या करें, क्या करें, ये तो चाहिए स्ट्रॉन्ग ई।
हम्म।
ये इसको कंट्रोल करते हैं, इसको नैरो बना लेते हैं
हम्म।
डोपिंग करके। ये नैरो हो गया, तो
या।
अब आपका ई तो बहुत हाई है,
हम्म।
डीएक्स आपका छोटा है, तो आपका डीवी क्या हो गया, छोटा हो गया। ये छोटा कर
हम्म।
दिया आपने, ये बड़ा ही है, तो डीवी कुल मिला के एवरेज आ गया।
हाँ।
अब आप ब्रेकडाउन वोल्टेज से बहुत ज्यादा दूर नहीं गए। So
हम्म।
you maintained high electric field, but because of the narrowness, your applied reverse potential is limited. You don't have to apply very high uh, reverse bias because the width is very high, right?
या।
So you are able to get very high voltage without applying too much, क्योंकि ज्यादा वोल्टेज लगाने से,
हम्म।
क्योंकि विड्थ बहुत ज्यादा है, तो वोल्टेज ऑटोमेटिकली बहुत बढ़ जाएगी हाई इलेक्ट्रिक फील्ड के केस में।
यस।
ई तो ज्यादा है और डीएक्स भी
हम्म।
ज्यादा है, तो वी बिकम्स वेरी हाई। वो
हम्म।
डिस्ट्रॉय कर देगा आपके, मतलब वो जो करंट है वो बढ़ जाएगा बहुत ज्यादा, तो
हम्म।
डिवाइस की इंटीग्रिटी खराब हो जाएगी। आप
हम्म।
कहते हो कि इलेक्ट्रिक फील्ड सेम रहे, यार मैं लेट मी नैरो इट विद द हेल्प ऑफ डोपिंग, सो माय वी
हम्म।
reduces overall. Now V is my limited, then I will not destroy the diode.
या।
पढ़ो, बाकी पढ़ो, क्लैरिटी होगी तो लिख
क्वांटम
पाओगे।
मैकेनिकल, हाँ।
ठीक है, चलो।
When the reverse voltage reaches the Zener voltage, the electric field across the narrow depletion region becomes extremely strong. This field enables tunneling of electrons from the valence band of the p region to the conduction band of the n region without needing thermal energy. The process is known as quantum tunneling. Yeah. Sharp increase in current, the tunneling of the electron results in the sharp increase in the reverse current, but the voltage across the diode remains nearly constant at the Zener voltage. Yeah,
इट इज
okay.
नॉट वेरी हाई रिवर्स बायस।
Hmm.
जीनर वोल्टेजेस होती हैं, वो कंट्रोल करा
Hmm.
आपने, उसको डोपिंग बढ़ा दी, इसको मैन्युफैक्चरर को बोला भाई मुझे यूज करना है ये
Hmm.
पीएन जंक्शन को रिवर्स बायस में,
Hmm.
तो मैं सस्ता काम करूंगा, आई विल गो एंड बाय नॉर्मल डायोड, व्हाई शुड आई
Yeah.
बाय जीनर डायोड, मैं कर ले। उसने लगा दी, वही हुआ, रिवर्स बायस वोल्टेज बढ़ गई क्योंकि इलेक्ट्रिक फील्ड हाई था,
Mm-hmm.
और जो रिवर्स बायस की वजह से इलेक्ट्रिक फील्ड बढ़ गया, और विड्थ भी
Yeah.
बहुत ज्यादा थी तो वोल्टेज बहुत नजर आ
Mm.
रही, खराब होगी
Yes.
डायोड। तो मैन्युफैक्चरर ने बोला अब आजा तो बेटा यहाँ पे मैं तेरे को नई डायोड देता हूँ जिसमें हेवीली डोपिंग करूंगा मैं,
हाँ.
इस पी और एन साइड पे,
हम्म.
तेरा डिप्लीशन रीजन तुझे नैरो देता हूं मैं, तो तू कम वोल्टेज में ही अटेन कर लेगा ज्यादा करंट।
हम्म.
करंट तो तुझे ज्यादा चाहिए ना, ले ले करंट ले ले, बट तेरी
हम्म.
वोल्ट डिवाइस खराब नहीं होगी।
या. ओके.
मैं रिपीट इसलिए कर रहा हूं सो दैट यू कैन अंडरस्टैंड इट एंड डोंट फील लॉस्ट।
या. या.
इवन इफ आई एम रिपीटिंग, बेयर बेयर विद मी, ये चलता है। Read it.
Occurs at a low reverse voltage. Zener breakdown typically happens below 5 years. Voltage regulations. Once Zener breakdown occurs, the diode maintains nearly a constant voltage, making it useful for the voltage regulation. Yeah. Non-destructive as long as the current is within the diode's rate. हाँ ठीक है.
खराब नहीं करना ना डिवाइस को.
हाँ
करंट पे भी काबू चाहिए,
काम नहीं करेगा या.
है ना. और वो कैसे काबू करते हो? जो वो जीनर वोल्टेज है वो छोटी रखते हो, करंट आपको मिल जाएगा कम वोल्टेज पे, नहीं तो आप खराब कर दोगे उसको.
Yes.
अगेन द सेम क्वेश्चन बट शॉर्टर फॉर्म.
Yeah. Occurs in heavily doped diodes. Mechanism quantum mechanical tunneling happens at low reverse voltage. Occurs in lightly doped material. Impact ionization happens at the higher voltage. Requires a wide depletion region. ठीक है.
सही है. अगर आपकी बर्फ अनकंट्रोल गिर रही है तो यू नो you may get killed because of that, right? You may get hurt. So what you do, you apply some nets on the way. तो उसकी स्पीड कम करते जाओगे ना, जैसे कंट्रोल कर लोगे उसको.
Yeah.
You are putting some control mechanisms on avalanche by increasing the diode or doping. Sorry. Where do you use it? Very important. Zener diode, basically what it does is very interesting. Okay, so you just see this one. Okay, for your, this is very important, protection. So there is a circuit, and you know that this circuit cannot tolerate a voltage beyond a certain voltage.
Yeah.
So what you do in this circuit is you put a mechanism of Zener voltage. Now what Zener voltage does is, if the sensitive component which cannot tolerate a certain voltage, what you do is you connect it with a Zener voltage. Zener voltage, supposingly a very high level of voltage comes to the sensitive device. If you have a Zener diode connected to it, the Zener diode does not allow the voltage to go beyond a certain value, because it starts increasing its current, but the voltage does not go beyond.
Okay.
You see the graph is like this, नीचे जा रहा है वो.
हाँ नीचे जाता है.
जो ब्रेकडाउन वोल्टेज है, ब्रेकडाउन वोल्टेज जो है, वो ब्रेकडाउन वोल्टेज जो होती है, अगर मान लो किसी ने 100 वोल्ट दे दी, डिवाइस 5 वोल्ट से ज्यादा टॉलरेट नहीं कर सकता. तो हम नहीं चाहते कि 100 वोल्ट 5 वोल्ट वाले डिवाइस तक पहुंचे. जीनर वोल्ट डायोड लगा दो उस डिवाइस के साथ. जैसी वो 100 वोल्ट की आएगी वोल्टेज, जीनर डायोड उसके सिर्फ 5 वोल्ट ही पास होने देगा. वो उसकी वोल्टेज बढ़ती नहीं उसके बियॉन्ड.
ओके.
सो ओवर वोल्टेज प्रोटेक्शन के लिए यूज जीनर ब्रेकडाउन.
Yes.
And electronics is all about sensitive. Mobiles are sensitive, laptops are sensitive. Any sudden change in the voltage can destroy the electronic devices.
Electronic, yeah.
Very sensitive. Projectors and all that. थोड़ा थोड़ा तो समझ में आ गया होगा, not too much.
नहीं यार, ये तो जीनर वाला avalanche तो ठीक है, 4 बार पढ़ के.
एक बार खुद भी पढ़ लेना.
हाँ नहीं
लिख लेना. ये क्वेश्चन मतलब यही आते हैं.
अच्छा जी, आपने जी मुझे दिखाए जी, लाइक जी नोट्स हैं,
हाँ,
इन्हीं को लर्न कर लूं तो काफी
बहुत है, बहुत है.
मतलब ऐसे लग रहा नहीं खोलूं ना फिर मैं इसके लिए.
नहीं,
ये
नहीं.
आपने दिखाए बस इन्हीं को रट लूं.
यस, यही क्वेश्चन होते हैं, है ही कुछ नहीं इसके अंदर.
ठीक है.
अगर somebody is saying you have to study VI characteristic, ग्राफ समझना है, तो ग्राफ पे लेबल करो. वो भी हो गया भाई, ये ब्रेकडाउन वोल्टेज है, यहाँ पे करंट बढ़ रहा है, ये फॉरवर्ड बायस है, ये रिवर्स बायस है ना. कहाँ पे यूज होती हैं ये, दिस इज मोर देन इनफ. VI कैरेक्टरिस्टिक्स
थोड़ी सी अलग
छोड़ दो,
लैंग्वेज.
छोड़ दो, छोड़ दो, छोड़ दो. उसकी लैंग्वेज होपलेस है. पर आपको ये वर्बटम लिखना है. अपने मन से नहीं लैंग्वेज बनानी है आपको।
नहीं, इसी को रट लूंगा ना जो दिखा
हाँ, मैं
रखा है।
अपनी लैंग्वेज बना ली, गलत हो जाएगा आपका। अच्छा, नाउ द क्वेश्चन अराइजेस
हम्म,
कि पी पी के अंदर होल होते हैं,
हाँ।
एन के अंदर इलेक्ट्रॉन्स होते हैं, तो
हाँ।
ये माइनॉरिटी चार्ज कैरियर देता कौन है?
हम्म।
आए कहां से, राइट? बहुत सिंपल है।
हम्म।
एक्चुअली क्या होता है कि जो पीएन जंक्शन डायोड तो बना लिया आपने, ठीक है, लेकिन क्या होता है कि जो
हम्म।
रूम टेम्परेचर होता है जब,
हम्म।
उस पे भी जो एनर्जी मिलती है,
हम्म।
तो इलेक्ट्रॉन्स जो होते हैं वो अपनी एटम को छोड़ के डिसलॉज हो जाते हैं।
हम्म।
पी साइड पे एटम्स हैं,
हाँ।
उन्होंने होल तो ऑलरेडी आपको दे ही दिया है,
हाँ।
उनका काम खत्म। एन
हाँ।
साइड वालों ने आपको इलेक्ट्रॉन एक्स्ट्रा दे दिया, उनका काम खत्म।
हाँ।
यही तो काम करते हैं ना पी और एन, अब एक एक्स्ट्रा
हाँ।
इलेक्ट्रॉन एक एक्स्ट्रा होल दे देते हैं, बोलते हैं मैंने
हाँ।
काम कर दिया जी, अब इससे काम करो। हमने
हम्म।
बोला नहीं, हम तो जी रिवर्स बायस में काम कर रहे हैं, तो तुम्हारे तो जो मेजोरिटी चार्ज कैरियर है वो तो फॉरवर्ड बायस में काम करते हैं।
हाँ।
इलेक्ट्रॉन तो पॉजिटिव साइड की चला जाता है और होल नेगेटिव
हाँ।
साइड की तरफ चले जाते हैं जब हम फॉरवर्ड बायस करते हैं। बट नहीं, हमें तो जी रिवर्स बायस में काम करना है। उसने बोला आई विल नॉट अलाउ, तो कहते कोई बात नहीं, तू तो देगा नहीं कुछ भी। तो
हम्म।
माइनॉरिटी चार्ज कैरियर कैसे पैदा होते हैं? जो रूम टेम्परेचर पे एन साइड पे,
हम्म।
इन साइड पे होल मिल जाते हैं बिकॉज ऑफ रूम टेम्परेचर, और एन
ओके।
साइड पे, सॉरी,
पी
और
पी
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 साइड पे इलेक्ट्रॉन मिल जाते हैं। यही जो एटम्स होते हैं, सिलिकॉन और बोरॉन, और सिलिकॉन और आर्सेनिक फॉर एग्जांपल, राइट, ये एन साइड पे आपको होल मिल दे देंगे और पी साइड पे आपको इलेक्ट्रॉन दे देंगे बिकॉज ऑफ थर्मल एनर्जी। मतलब इलेक्ट्रॉन पी साइड पे अपने एटम को छोड़ देता है बिकॉज ऑफ,
हाँ। ओके।
एक्सपेक्टेशन तो यह है कि पी साइड है, ये तो होल
हम्म।
देगा, लेकिन थोड़ी बहुत हीटिंग होती है रूम में, उससे जो थर्मल एनर्जी होती है,
हम्म।
उससे वही लोग जो हैं वो इलेक्ट्रॉन भी दे देते हैं, थोड़े से,
ओके।
थोड़े से, ज्यादा नहीं, ज्यादा तो
हम्म।
पी देते हैं।
ओके।
पी की क्वांटिटी जबरदस्त मिलेगी,
हम्म।
क्योंकि भाई बोरोन है, उसने तो अपना काम यही करना है,
हम्म।
होल देने का। आर्सेनिक है, उसने इलेक्ट्रॉन देने हैं।
हम्म।
लेकिन ये लोग थोड़े थोड़े अपने होल्स और इलेक्ट्रॉन्स भी दे देते हैं बिकॉज ऑफ थर्मल
हम्म।
जनरेशन ऑफ इलेक्ट्रॉन होल पेयर।
ओके।
नाउ रीड दिस कि व्हाट इज द सोर्स। तो अवलांचे ब्रेकडाउन इज ऑल द करंट इज द माइनॉरिटी, रिमेंबर।
हम्म।
तो माइनॉरिटी देने की शुरुआत तो करनी पड़ेगी ना।
यस।
सारा पड़ा हमने पी बना दिया जी, होल होते हैं बड़े सारे, अब इलेक्ट्रॉन एक्स्ट्रा हो जाते हैं, अब
हम्म।
कंडक्टिविटी में सुधार हो जाएगा। सिर्फ सिर्फ नॉर्मल सिलिकॉन और जर्मेनियम की कंडक्टिविटी काफी नहीं है।
हम्म।
पढ़ो इसे,
Majority carriers are the dominant type of charge carriers.
यहां से
P
पढ़ो,
type.
यहां से स्टार्ट फ्रॉम हियर।
Okay. Minority charge carriers in a P junction. PN junction are produced due to the thermal generation of electron holes pair within the semiconductor material. Has it? Majority carriers are the dominant type of charge carriers. P type majority carriers are hole. N type electrons and minority carriers less abundant type of charge carriers. उल्टा हो जाता है ना, बस पी में इलेक्ट्रॉन देन एन में होल्स। या ओके।
यस, पी में मेजोरिटी इज होल।
हाँ।
तो आपको ग्राफ बनाने को बोल सकते हैं, मेक अ ग्राफ,
हम्म।
फॉरवर्ड बायस, रिवर्स बायस, एक्सप्लेन द ग्राफ, राइट द सेम थिंग।
या।
सब कुछ सेम, फॉरवर्ड बायस क्या होता है, रिवर्स बायस क्या होता है, इसमें मिली एम्पियर में होता है, इसमें ये होता है, वो ऊपर वाला जो ग्राफ है वो मेजोरिटी कैरियर की वजह से है करंट,
हम्म।
राइट, ये माइनॉरिटी कैरियर की वजह से, एक्सेट्रा एक्सेट्रा।
हम्म।
जितना भी पढ़ा सब लिख दो।
या।
व्हाट इज द यूज ऑफ अ जीनर डायोड? वोल्टेज प्रोटेक्शन, ओवर
हम्म।
वोल्टेज प्रोटेक्शन।
या।
overall graph, how will it look? Which you need to draw. Okay, and I will. Look at this. I'm going to the next page now because I think. Look at the graph. यहाँ पे आपने 0.7 वोल्ट को फोड़ा forward bias में.
हाँ.
And you're able to get huge current, good current. So now you are using the diode with zero resistance. It is offering no resistance. Good current is flowing. Very good.
Yes.
So this is your VF, V forward.
हम्म.
You have to mark all of this, V forward and all
हाँ
that,
तो
right?
ये वही दोनों ग्राफ को ज्वाइन कर दिया ना उन्होंने.
Join कर दिया बिल्कुल. ये है I forward,
हाँ.
I reverse,
हम्म.
V reverse. ये वो वाली वोल्टेज है. नी दिख रहा है जहाँ पे नी.
Yes.
नी दिख रहा है नी. दिस इज अ ब्रेकडाउन वोल्टेज. यहाँ नी बन रहा है घुटना. जैसे यहाँ पे भी घुटनी है बट इतना घुटना नहीं है जितना ये है. जैसे हम कुर्सी पे बैठते हैं तो घुटना ऐसे होगा ना शेप.
हाँ जी. Yes.
तो ये घुटना है.
या.
आप कुर्सी पे बैठे हो, ये घुटना नहीं हो सकता ऊपर की तरफ. घुटना नीचे की तरफ ही होगा. तो जस्ट अ वर्ड, राइट. नी, नी से डरना नहीं है. इट इज जस्ट अ शेप. दिस शेप इज नी.
Yes.
They will ask you to mark it, explain forward bias क्या होती है, reverse bias क्या होती है, reverse bias में क्या क्या होता है, नी वोल्टेज पे क्या होता है, ब्रेकडाउन हो जाता है. ब्रेकडाउन क्या होता है जी? अवलांचे ब्रेकडाउन ये होता है. फिर उसको सुधारें कैसे? जीनर से करते हैं. वो कैसे करते हैं भाई? डोपिंग बढ़ा देते हैं, वोल्टेज को, सॉरी, डिप्लीशन रीजन को नैरो कर देते हैं. नहीं?
Yes.
तो वही कहानी. क्वेश्चन ऐसा है, एक्सप्लेन द वीआई कैरेक्टरिस्टिक. वीआई ग्राफ बनाया, पूरी गाथा लिखी.
Yeah.
उसमें छोटा पार्ट आ गया, एक्सप्लेन ओनली जीनर. ले लो जी, जीनर ले लो. एक्सप्लेन ओनली अवलांचे ले लो, अवलांचे ले लो.
ठीक है.
1 मार्कर, 2 मार्कर, कुछ भी बना सकता है.
Yeah.
जो जीनर डायोड होती है, there is a way to show the Zener diode. Okay, there is a certain diagram which you have to use for Zener diode. I will show you how you show a Zener diode. Zener diode ऐसे नहीं बनती, वो ट्रायंगल और डंडा. उसका ना एक जो डंडा होता है वो टेढ़ा कर देते हैं थोड़ा.
Okay.
I will show you how it is made actually. Okay, so this is the way a Zener diode. If they say explain a Zener diode, then you will have to make the. ये देखो क्या करा है इन्होंने. ये तो नॉर्मल डायोड है, ये P है, ये N है.
हाँ.
लेकिन ये वाला दिख रहा है आपको? ये डंडे दिख रहे हैं, ये वाले. एक डंडा बाहर, एक डंडा अंदर. अगर ऐसी डायोड नजर आ जाए तो इट्स अ जीनर डायोड.
अच्छा, ठीक है.
ग्राफ देखो, ग्राफ देखो. यहाँ पे इसने नीचे क्या दिखा रखा है? आई जेड. है तो जीनर अब ये जीनर ऑपरेशन हो रहे हैं. एक पर्टिकुलर वोल्टेज के बाद वोल्टेज बढ़ना बंद होगी और करंट बड़ा ड्रास्टिकली बढ़ा. बट वो खराब नहीं होगी क्योंकि ये लो वोल्टेज पे कर दिया आपने. नैरो विड्थ एंड हाई
वोल्टेज.
डोपिंग. वोल्टेज हाई नहीं जानी चाहिए, वो अवलांचे में चली जाती है बहुत ज्यादा.
ठीक है.
कंट्रोल्ड है अभी.
हाँ, ठीक है.
राइट. सो दिस इज जीनर ऑपरेशंस. ये वाला पार्ट जो है जीनर ऑपरेशंस है, ये वाला.
हाँ, अंडरस्टूड.
नी के बाद.
हाँ, ठीक है.
लेट मी.
I think is this the last topic for this chapter?
No.
अच्छा.
डायोड बड़ा टॉपिक होता है थोड़ा,
हम्म।
जल्दी ना हो जाओ।
नहीं नहीं, पूछ रही थी मैं तो सिर्फ।
Okay, does the when the diode is in forward bias
हम्म
and we draw the IV characteristic, does
हम्म।
it follow Ohm's law?
नो,
एक्सपोनेंशियल वाला।
वो इक्वेशन होती है ना।
हाँ, वही वाली ई रेस टू पावर, वो उसको
हाँ,
फॉलो करता है।
आई इज इक्वल टू आई एस
हाँ, वो ऊपर जो आता है
पावर में, हाँ,
सैचुरेशन
क्यू
ई रेस
बी
टू पावर
अपॉन।
समथिंग। हाँ,
हाँ।
याद कर लेना।
हम्म।
ओके, वन मोर, ओके, डिस्कशन। सो पीएन जंक्शन डायोड की एक एप्लीकेशन, सॉरी जीनर की हमने एक एप्लीकेशन पढ़ी, which is the application called as a over voltage protection, right?
यस।
But the normal diode, which is a normal PN junction diode, right?
हम्म
We say a normal junction diode is basically a switch.
हम्म
A normal junction diode is a switch.
हम्म।
Why?
Listen, repeat.
A normal PN junction diode is a switch. Why do we say that? On off का क्या काम करता है वो? Wait, just give me 1 second.
हाँ ये।
Just give me 1 minute.
Yes, sir.
हाँ जी, आई एम बैक।
यस सर।
हाँ जी, पढ़ा आपने ये?
मेरे को अब दिखा ये, अब लोड हुआ जैसे आपने हिलाया।
ओके, देखो क्या है जो
स्विच
हमने
ऑफ ऑन
फॉरवर्ड।
बटन वाला है ना?
हाँ,
अच्छा।
फॉरवर्ड बायस के अंदर
हम्म।
करंट फ्लोस,
हम्म।
इट इज ऑन।
या एंड इन
रिवर्स बायस में द करंट डज नॉट फ्लो, सो इट इज ऑफ।
it's at the switch on and off button.
हाँ, पढ़ लो ध्यान से।
हाँ. When the P junction is connected to the positive terminal of the voltage source and the N region is the negative, the diode is said to be forward. In this condition, the depletion region narrows and the built-in potential barrier is reduced. Once the applied voltage exceeds the threshold voltage, the diode conducts current. The diode allows the current to flow, acts as a closed switch.
जी,
अच्छा, in forward it acts as a closed switch.
या क्लोज स्विच हो गया ना, सर्किट फ्लो,
हाँ,
करंट फ्लो
हाँ,
कर रहा
करंट फ्लो कर रहा है.
है,
When the
ओपन
P,
सर्किट।
yeah,
आपने इसको रिवर्स बायस कर रखा है।
हाँ ठीक है. When the P,
क्वेश्चन है बायसिंग का, छुपा के उसे चेंज कर दिया, स्विच बना दिया उसको।
हाँ, yeah,
वेरी क्लेवर।
yes.
बट ये बेसिकली यू हैव टू नो बिकॉज सम पीपल कॉल इट अ स्विच ऑल्सो। इसका
हम्म.
इस्तेमाल क्या होता है? पीएन जंक्शन डायोड तो तुमने जीनर में यूज कर ली एक जगह पे, है एक जगह
हाँ.
तुमने उसको रेक्टिफायर यूज कर लिया, बस यही है। तो
हम्म.
बताओ, नहीं यार, जीनर डायोड रिवर्स बायस वाला भी पता है हमें। वी
हम्म.
ऑल्सो नो कि ये ओवर वोल्टेज प्रोटेक्शन के काम आता है,
हम्म.
जीनर डायोड। और दूसरा हमें एक और एप्लीकेशन मालूम है कि नॉर्मल पीएन जंक्शन कैन बी यूज्ड एज अ स्विच।
Yeah.
नॉर्मल है ना, बिल्कुल, मतलब कुछ नहीं करा है इसमें।
हम्म.
आई एम जस्ट लुकिंग इनटू सीबीएसई पेपर्स। यार सीबीएसई के पेपर में
हम्म.
220 देख रहा हूं मैं, 2021 का। हाँ देखो, आया क्वेश्चन नंबर 5। अभी हमने रेक्टिफाई नहीं करा, उसे तो छोड़ दो आप, बट लेट मी शो यू वन ऑफ द क्वेश्चंस इन 20। डोपिंग हम कहाँ बढ़ाते हैं, कौन सी डायोड में?
क्या?
डोपिंग पढ़ो, क्वेश्चन पढ़ो।
एक बार हिलाना कर्सर.
एक मिनट, आ गया है।
और लोड हो रहा है.
ओके,
नहीं आ रहा सर, ये आपको एक बार वापस करो उसको. How does the width of the depletion of the PN junction vary if doping?
हमने देखो जीनर डायोड के केस में हाई डोपिंग रखी थी,
हाँ, जीनर में
और
बढ़
हमने
जाएगा.
बोला था नैरो हो जाएगा।
हाँ.
तो ये देखो, इनडायरेक्ट क्वेश्चन है, इट विल
इसमें ये
नैरो।
बता लेंगे जीनर में डोपिंग ज्यादा होती है एंड अवलांच इट्स लेस.
हाँ, लेकिन इसमें क्वेश्चन है कि हाउ डज द विड्थ ऑफ द डिप्लीशन रीजन इम्पैक्टेड बाय डोपिंग से विड्थ ऑफ द डिप्लीशन रीजन पे क्या फर्क पड़ता है? भाई, डोपिंग बढ़ाने से विड्थ कम हो जाती है ना,
हाँ.
डोपिंग बढ़ाने से विड्थ कम होती है जीनर की।
हाँ.
जीनर में करते हैं सभी, राइट? वो
यस.
पूछ रहे हैं हाउ, कैसे? भाई आपने डोपिंग कर दी तो नैरो क्यों हो जाती है विड्थ, राइट? वो बोल रहा है वो। नैरो तो हो जाती है, बोल दिया ना हमने, तो नैरो होती है।
हाँ,
बट सवाल ये है कि भाई
कि कैसे
क्यों
हो?
होती है नैरो? नैरो क्यों करते, कैसे करते हो नैरो? चलो डोपिंग कर दी मैंने, बढ़ा दी। हाउ डज इट हेल्प यू टू रिड्यूस द डिप्लीशन रीजन?
इनवर्सली होता है वो उसके।
सोचो, आपने डोपिंग कर दी, मतलब आपके जो इम्प्योर
हाँ।
एटम्स है वो आपने बढ़ा दिए,
हम्म।
इम्प्योरिटी बढ़ा दी, तो क्या हो जाता है हाई इम्प्योरिटी से?
मतलब हाई डोपिंग से तो क्या बोलते
नैरो
हैं, डिप्लीशन लेयर भी डिक्रीज हो जाती है, विड्थ डिक्रीज हो
डिक्रीज होती है,
जाती
राइट? हाँ, वो कहता है क्यों, राइट? क्यों होता है ऐसा, राइट?
है।
क्यों होता है?
हाँ।
अब से देखो कैसे, क्या लिखोगे आप? वाई दिस हैपेंस, इसका अगर आपको आंसर लिखना है,
हाँ।
राइट एन आंसर, राइट? सो यू डोंट नो द मैथ्स, यू ओनली नो द थ्योरी। मैथ्स तो आती नहीं हमें इसकी, डोपिंग की। पढ़ो, देखो क्या होता है। सबसे पहले आपने जब डोपिंग करी तो आपने क्या करा, जो चार्ज कैरियर
हम्म।
कॉन्सेंट्रेशन है आपकी वो बढ़ गई।
हाँ।
इम्प्योरिटी की वजह से आपके पास जो इलेक्ट्रॉन्स और होल्स हैं वो बढ़ गए।
हम्म।
डोपिंग का तो काम ही यही होता है,
हाँ।
एक्स्ट्रा होल देना, एक्स्ट्रा इलेक्ट्रॉन देना।
हम्म।
आपने डोपिंग की मात्रा बढ़ा दी, इम्प्योरिटी ऐड कर दी,
हम्म।
तो क्या हुआ देखो, एन रीजन में फालतू इलेक्ट्रॉन और बढ़ गए।
हाँ।
एन रीजन में तो इलेक्ट्रॉन ही होता है मेजोरिटी,
यस।
वो भी बढ़ गए। और आपने जब होल्स थे आपके, वो भी बढ़िया मिल गए आपको। ठीक है।
हम्म।
अब क्या हुआ, सिंस द डिप्लीशन रीजन forms to balance the electric charge between P and N region. A
हम्म।
higher means the required number of recombination happens over a short distance. Finally तो क्या होगा, जब इनको आप जोड़ोगे पी एन जंक्शन को, तो एक इधर उधर डिफ्यूजन होती जाएगी, और एक लेवल के बाद डिप्लीशन
हम्म।
का जो सेंटर है, मतलब वो लाइन, उसके दोनों
हाँ।
तरफ आयंस आ जाएंगे, और
हम्म।
फाइनली उनका क्या काम होगा, वो दूसरे उस तरफ से आने वालों को रोक देंगे।
हाँ।
अब क्योंकि आपकी कॉन्सेंट्रेशन इतनी ज्यादा है, तो
हम्म।
थोड़ी सी देर में ही बहुत सारे उस तरफ चले जाएंगे, क्योंकि आपके पास बहुत बहुत अच्छी क्वांटिटी ऑफ इलेक्ट्रॉन, और उस साइड बहुत अच्छी क्वांटिटी ऑफ होल्स है,
ओके या।
राइट? तो फास्टर डिफ्यूजन विल हैपन।
हम्म।
तो आपकी जो डिप्लीशन लेयर है ना, ज्यादा
हम्म।
चौड़ी हुए बिना थोड़े के अंदर ही, क्योंकि ज्यादा आपके पास मात्रा ज्यादा है,
हम्म।
और उतने टाइम में आप ज्यादा चले जाते हो, तो आपको ज्यादा डिप्लीशन लेयर चौड़ी करनी नहीं पड़ती।
हाँ।
आराम से करोगे अगर डोपिंग कम है। If you do it slowly, then the depletion region will become quite broad, because
यस।
you will take some time to attain the equilibrium,
हम्म।
and then the electric field will come and then it will stop. But if you have higher charged, in 0.1 second you are able to cross over double the number of electrons and double the number of holes.
हम्म।
So within a small area itself, the high electric field will come,
या।
depletion layer, right? So the high electric field will stop immediately.
यस।
So the you are able to attain the charge balance, right?
या।
Very fast with a narrow depletion layer.
ओके।
भाई आपको टोटल जो है 40 होल चाहिए थे उस तरफ डिप्लीशन करने के लिए, और
हम्म।
40 इलेक्ट्रॉन चाहिए थे इधर डिप्लीशन लेयर करने के लिए। इलेक्ट्रॉन इधर का इस तरफ के वो होल खा गए, और
यस।
होल उस तरफ गए उस तरफ के इलेक्ट्रॉन खा गए, तो आयंस आ गए दोनों साइड पे।
हम्म।
अब आप कहते हो जी इतने टाइम में तो 0.5 सेकंड में कर लेंगे हम तो इसे, तो आपकी डिप्लीशन जो है, अब आपको चाहिए 40-40।
हाँ।
पहले आपकी उससे जो होता था टाइम लगा के, डिप्लीशन लेयर मोटी मोटी बनती थी दोनों साइड पे आयंस की।
हाँ।
अब आपका 0.5 सेकंड में चला जाता है, तो डिप्लीशन रीजन इतनी चौड़ी हो नहीं पाती। वो रिकॉम्बिनेशन जो होती है न्यूट्रलाइज करने वाली, वो कम रीजन में ही हो जाती है, क्योंकि अब गए तो 40 अभी भी,
हम्म।
लेकिन आधी विड्थ में ही हो गया सारा काम।
या।
सो यू आर एबल टू अटेन द चार्ज बैलेंस।
अंडरस्टूड या।
इलेक्ट्रिक फील्ड पैदा हो जाता है और फिर रोक दिया, अब अपने सब बैलेंस हो गया, इक्विलिब्रियम हो गया,
ठीक है।
राइट? तो व्हाट यू डू, द डेंसिटी ऑफ immobile ions increases. Remember that the immobile ions are coming from arsenic and boron.
बोरोन।
अगर आप ज्यादा उनकी डालोगे तो इमोबाइल आयंस भी तो बहुत बढ़ जाएंगे ना लेयर पे।
हाँ।
तो जो 40 आयन दो लेयर में बनते थे पहले,
हम्म।
दो लेयर में दोनों साइड पे, ये यहाँ पे मान लो आपकी बोरोन है और दूसरी साइड एन साइड पे आर्सेनिक है, ऐसे बनती थी। तो आपकी जो नेट बनी आपकी जो वो डिप्लीशन रीजन इतना चौड़ा हो गया आपका, वो सेंटर है उसका, राइट।
हाँ।
मैं सेंटर का कलर दिखा देता हूँ। अब आप चौड़ाई देखो इसकी क्या है, ये इस साइड कितनी है और इस साइड कितनी है, टोटल तो बहुत चौड़ा हो गया।
यस।
एक तरफ आर्सेनिक के आयंस हैं और एक तरफ बोरोन के आयन है।
हम्म।
ये आर्सेनिक के आयंस हैं, ये बोरोन के हैं, राइट। अब आपने क्या करा, आपने डेंसिटी ऑफ जो वो है आर्सेनिक और बोरोन ज्यादा डाल दी थी, क्योंकि आप कंसंट्रेशन बढ़ा रहे हो, डोपिंग इंक्रीज कर रहे हो। तो
हम्म।
आर्सेनिक ज्यादा अवेलेबल है, बोरोन ज्यादा अवेलेबल है। अब आपने हायर उसके साथ करा, तो ये जो टोटल थे, 1 2 3 4, ये मान लो 40 थे
हम्म।
और ये भी 40 थे। अब ये 80 अवेलेबल है।
हाँ।
तो ये क्या करेंगे, ये 80 जो है, क्योंकि आपके पास ज्यादा है अब अवेलेबल,
हाँ।
मात्रा अवेलेबल ज्यादा है, तो ये एक ही लेयर में 40 दे देंगे आपको। दो लेयर नहीं बनानी पड़ेगी इनको। दे विल गिव यू द सेम नंबर ऑफ ions in one
हम्म।
layer because they are large in number ना।
यस।
टू अटेन अ बैलेंस यू नीडेड 40, तो आपने एक चौड़ी लेयर बना के 40 कर लिया अपना।
हाँ।
लेकिन अगर आपके पास कंसंट्रेशन ऑलरेडी ज्यादा है तो 40 आपको एक ही लेयर में मिल रहा है। तो
हाँ।
आपकी ये जो है विड्थ नैरो नहीं होगी।
हो गई।
तो आपने जो चार्ज बैलेंस आपने जल्दी अचीव कर लिया, छोटी सी डिप्लीशन हुई और हो गया, क्योंकि नंबर ऑफ क्वांटिटी बहुत ज्यादा अवेलेबल थी।
हाँ।
या तो भाई धीरे धीरे रोटी खा लो और पेट भर लो, या सीधा
हम्म।
कर लो 40 रोटी,
हम्म।
तो जल्दी कर लिया ना आपने।
हम्म।
तो इसीलिए डोपिंग से, क्योंकि आपके इमोबाइल चार्ज कैरियर्स आर ऑल्सो वेरी हाई इन क्वांटिटी,
हम्म।
यू आर एबल टू गेट अ रिलेटिवली नैरो डिप्लीशन रीजन।
या ओके।
ये आपकी की लाइन है। अगर ये आंसर लिख दोगे आप, यू डन।
ओके।
With high doping, the density of immobile ions increases.
हम्म।
So the same electric field can be established with the answer.
या ओके।
देखो सीबीएसई वाले बहुत मतलब गहरे गहरे क्वेश्चन जो होते हैं ना, इसलिए इसके 1 मार्कर और 2 मार्कर फिर भी पढ़ लेना।
हम्म।
बहुत सारे होते हैं, थ्योरी मत
हाँ।
पढ़ना। वन
हम्म।
मार्कर 2 मार्कर पढ़ना, उसमें आपको रेडी Q&A मिल जाता है ना।
ठीक है। हाँ।
ठीक है जी। तो
हाँ
अब हम क्या
जी।
करेंगे, आई थिंक व्हाट वी हैव कवर्ड सब्सटेंशियल ग्राउंड ऑन वी आई कैरेक्टरिस्टिक ऑल्सो। अब हमें पढ़ना है डायोड एज अ रेक्टिफायर।
ठीक।
डायोड एज अ जीनर डायोड हमने पढ़ लिया।
हाँ।
मैंने आपको शुरू में रेक्टिफायर से इंट्रोड्यूस कर लिया था, मैं उसको फॉर्मल वे में थोड़ा और आपको इंट्रोड्यूस कर दूंगा। फिर मैं आपको उस पर न्यूमेरिकल प्रैक्टिस करवा दूंगा और 2 3 और कॉन्सेप्ट्स को रिवाइज करवा दूंगा मैं आपको।
ठीक है।
रिवाइज मतलब दोबारा, थोड़े
ठीक।
और डिटेल में। ठीक है जी। अब व्हेन आर यू अवेलेबल नाउ?
I'll tell you the timings for tomorrow.
नॉट टुडे, बाद में।
टुडे अगर टाइम मिलता है तो I'll message you
अगर
in
होगा तो मैं बता
advance.
दूंगा आपको, ठीक है।
हाँ।
डिपेंड्स, मे
ठीक
नॉट
है।
बी अवेलेबल इन द इवनिंग आफ्टरनून, पर आप मुझे बता देना अगर अवेलेबल हो, कोइंसाइड करेगा, वील हैव अ क्लास।
ठीक है। ओके।
ठीक है।
हाँ जी। यस। ओके।
दिस इज मोर देन इनफ नाउ।
हम्म।
सी यू देन, बाय।
ओके बाय। थैंक यू।